Hello, my name is Hyun Kim. I'm new graduate student at this year from PRMN lab working with Professor Lee. I begin my presentation from now on. My presentation consists of those contents: my goal, selected paper, application and result of my data, my proposal, and result. I participated in the hackathon held by Korea University in January at this year before I entered this university. The goal of this hackathon was to identify injection molding machine dataset and detect defective data. When the data were refined, less than 80 out of approximately more than 10,000 data were defective. I did get good result. At that time, I only knew the traditional classification and I didn't know the concept of closed set and open set. At that time, it ended without solving the question. But through this class, I learned that the concept of open set and the hackathon addressed the problem that was anomaly detection. Now I know. Therefore, my goal is to solve the data set that I couldn't solve at that time using the paper I led this time. The data are injection molding machine datasets and are guided by following features and characteristics. The definition of this dataset is as follows. Injection molding is a plastic molding method in which thermoplastic is heated and injected into the cavity of the mold to cool it down in the mold when it is in a state of flux. Next, characteristics of this dataset as follows. First, the plastic surgery cycle is short, and the plastic surgery efficiency is good. Second, formation of a wide range of lesions. Third, automatically controlled. Fourth, large cosmetic products that are now available for molding. Fifth, available complex shapes because of high precision. The papers I read are those. I decided to apply the most recent paper and the classification-based anomaly detection general data paper codes that can be tried with tabular data rather than only image data. I also choose to apply classification-based method, not only reconstruction method like autoencoder AE, VAE, AAE, which is two most commonly used. Let me briefly review this paper again and related work. Deep SVDD aim to find the smallest sphere surrounding normal data through feature space of data learned based on deep learning. The mean average value of the output value determines the center of the sphere. Next, related paper, GOM, of deep anomaly detection using geometric transformation paper generates self-labeled and data obtained through geometric transformation for one class, runs a typical classifier and determines whether it is normal or abnormal from the classifier's score. This method originated from the motivation that classifier learns to distinguish between what transformation geo-transformed images have been applied to normal data to obtain a common feature for normal data. Then the model will output the following scores for normal data. The model will output the scores above for abnormal data. The algorithm GOAD, GOAD of classification-based anomaly detection for general data, follows application not only for image data but also for tabular data. In that way, geometric transformations were transformed into affine transformation. I checked the codes provided the paper. The quote of the paper is illustrated as follows. The paper makes affine transformation of the data. It gets the loss value using the mean of value passed through the network such as deep SVDD, and the loss with the transformation labels such as GOM to obtain the total loss. I first learned GOAD with the cyber attack benchmark dataset KDD data provided with the code. The code provided in this paper did not provide any chart and didn't test the valid data by saving the model. So I divided valid data and tested it. In only one epoch, the loss value was that, and for test data, F1 score was that, and accuracy was that about test data set. I checked that the result came out very well when I applied the valid data to save model. Here are the results for my data, the hackathon data. Since some epoch, the loss value has been converging between 1 and 0.5 after some epoch, and it has not improved. The F1 score was between 0.5 and 0.6 and was not better. I solved the problem by changing from standard scaling to min-max scaling, and the result came out well. The test data and valid data. I thought it would be meaningful to apply the transformed data to autoencoder, so I applied it as follows. I added reconstruction loss to the existing total loss. Before that, I applied autoencoder to the data. Data has not been transformed. As a result, I got a good result. This time I applied the transformed data to autoencoder. Loss failed to converge to near zero. Therefore, the model I designed didn't produce good performance either. It took much longer for the test dataset to F1 score to be 1 than for the existing GOAD method, and longer to train per batch size than autoencoder. For injection dataset, my dataset, autoencoder without data transformation had only 2 epochs for test dataset until the F1 score became 1, and it took only 24 seconds for 25 epochs. GOAD had only 3 epochs until the F1 score became 1 for the test dataset, and it took 35 seconds for 25 epochs. My model has 25 epochs until the F1 score became 1 for the test dataset, and it took 35 seconds for 25 epochs. It was my first time experiencing the kind of experience through this class, and it was a very meaningful time for me. Also, this experiment has failed. I believe that the method I proposed will certainly result in meaningful result. So I will try more it if time allows. Thank you for your attention.